So we just learned that for discrete random variables x and y, finding w equal to g of xy, finding its PMF was kind of a simple bookkeeping problem. Straightforward, maybe a little tedious, but not too difficult. So now we'll move on to the more difficult case when in fact we have x and y continuous, and the result will be typically of that w is also continuous, and we want to find the CDF and also the PDF of w. A good place to start here is our first continuous random variable, the spinning pointer from the beginning of chapter 4. In that problem, the spinning pointer position x was a continuous uniform 0, 1 random variable. So it had a continuous uniform PDF. And, um, and now we're going to assume that this x was the pointer on the circumference of a 1 meter circle. And now we're going to measure that in centimeters. So to do so, we do kind of a simple units transformation. If x between 0 and 1 is the distance in meters, then w is equal to 100x, transforms that into a measurement in centimeters. And our goal is to find the PDF of w. Later on, we'll have a theorem for the PDF of w, but to get started, it's better to derive the PDF. And to derive the PDF, we have a two-step procedure. One, we derive the CDF of W. And two, we take a derivative to find the PDF. Whenever you get stuck on a problem that involves finding a PDF, my suggestion is you always use this two-step procedure unless you've specifically learned a situation where you have a theorem that applies. For this problem, W equals 100x is a simple enough formula that we can solve directly for the CDF of W. Specifically, we write the CDF of W is the probability W is less than or equal to little w. And then we just simply know that the W is equal to 100x. That's its definition, is less than or equal to W. And now we can rearrange this to say that this is x is less than or equal to W over 100. And now we have that this is equal to the CDF of x evaluated at W over 100. The next step is to recall that when we have the continuous uniform PDF of x, which is 1 from 0 to 1, we in fact already know that the CDF of x is the ramp function fx of x, which is 0 for x less than 0. It's equal to x for 0 less than or equal to x less than or equal to 1. And it's equal to 1 for x greater than 1. And now we can just simply substitute in the CDF of W is the CDF of x at W equal over 100. And we can just simply take the right side of the CDF of x and plug in W over 100. uh, x W over 100. This kind of macro substitution uh, is surprisingly powerful and effective. And now all we have to do is kind of rearrange these cases. The values of the cases, 0, W over 100, and 1 don't change. But on the right side, the case statements you would rewrite as W over 100 less than 0 is just W less than 0. And the second case is W has to be greater than or equal to 0, less than or equal to 100. And finally, W greater than 100. Now we're almost done. We finish the problem by taking a derivative. And we do that case by case. And the only case that actually matters is that the middle case of W from 0 to 100. And we obtain the derivative of W over 100 with respect to W is 1 over 100. And 0 for the other two cases of when the CDF is either 0 or 1. So we see that the answer is more or less what you would have guessed the answer to be, that if when we measure something in meters and it's a uniform 0 to 1 continuous random variable, when we measure it in centimeters, it's still a continuous uniform random variable, but it's continuous uniform from 0 to 100. And this problem is pretty simple, and but it shows you that when you do these units translations, you kind of have to be careful to make sure that the numbers work out okay. It's also worth pointing out that we solve this problem essentially just by doing algebra and rearranging the probability W is less than little w into the probability X is less than something with respect to W, and then there was just some algebra to do the rest. If you read the textbook and you'll see that the approach in the book is somewhat different. It follows kind of a graphical procedure, and this is worth talking about because as you get to trickier problems, this sort of graphical insight is useful. So here is the solution in the book. You'll see that there's a lot of words here, and if you read the words carefully, it'll provide you kind of a way to think graphically about this problem. And essentially, let's talk through what these words say. So so the point here is that um, there is a function which is that W is equal to 100x. And our goal here is to find the Cdf of W, which is the probability W is less than or equal to W. So what we do here is we mark a value of W, and and the way to think now about this problem is that we're interested in what is the probability that we observe a W that is below this little w. So if we think about points in the w-axis, it's all these points down here. And what the function w equals 100x is that it connects this to the same values of x that give you w less than equal to w. It's these values of x, right? And and so graphically, what has happened here is that the event w less than or equal to w is the same as the event x is less than or equal to w over 100. Before, we did this just kind of algebraically on the previous slide, but here we're really making the point that like the region the set of w's on the w-axis corresponds to a set of x's on the x-axis. And for this function, the mapping is really simple, but we'll see for other problems that it can be more complicated. Now, the rest of the problem is essentially the same. We have the Cdf of W. It's probably W is less than W. Probably 100x is less than W. Probably x is less than equal to W over 100. Cdf of x at W over 100. And this slide finishes the problem, and it has exactly the same algebra that we did on the first slide. So this number 100 isn't special, and we generalize that in this theorem to W is AX, where A is any constant greater than 0. So this is typical for any units conversion. For example, if X is kilometers and W is meters, then A would be 1,000. And the, the theorem we get is that the CDF of W is the CDF of X at W over A, and the PDF of W is the PDF of X at W over A, but there's this scaling factor 1 over A. And the need for this scaling factor is to ensure that the area under the curve of the PDF of W integrates to 1. Before moving on, it's just important to note that this theorem requires a greater than 0. If a is less than 0, right, the theorem is wrong. The generalization to negative a will occur later. If a is equal to 0, then w is going to be a discrete random variable that's also always 0. There'll be essentially a PDF of w will be an impulse at 0. And once again, the theorem is wrong. The theorem is only correct for a strictly greater than 0. So this example demonstrates the theorem, and using the theorem, we have directly that the PDF of W is 1 over A, the PDF of X at W over A. So this is not quite as simple as it looks. In particular, the CDF of X at W over A, we can find that by kind of macro substituting W over A for X. So it's 2W over A, 0 less than or equal to W over A less than or equal to 1, 0 otherwise. And so this is 2W over A, 0 less than or equal to W, less than or equal to A, 0 otherwise. And then the next step is that we know that we have to account for this factor of the 1 over A here. And when we put that into our solution, we get this is 2W over A squared, 0 less than or equal to W, less than or equal to A, and 0 otherwise. So this is the solution. And algebraically, it's not too complicated, but the problem asks you to sort of plot this solution at a as a half, and at 1, and at 2, just to show you how the shape of this PDF kind of changes fairly radically as you uh, change the value of a by doubling it twice. So this slide's from the textbook. Where the plot is better than what I could draw by hand. And the point to note here, for instance, is that when A is equal to 2, this is kind of a very flat ramp. And when A is equal to a half, right, it's a very tall triangular ramp. And the reason is because the area under the PDF has to always be equal to 1. So if we have a ramp, in either case that starts at 0, when the ramp is from 0 to 2, it can't rise very much because the area under the curve has to be 1. On the other hand, when you choose A to be small, like A is a half, then the PDF is defined from 0 to a half, but the ramp has to be very tall in order to have area under the curve uh, equal to 1. It's just good to keep in mind that PDFs don't have any limitation on their maximum value. Specifically, they can be a lot bigger than 1 if, in fact, the random variable x is concentrated. And that concentration isn't unusual. It just, in this case, for instance, corresponds to choosing a units where you're measuring something with small numbers. So we've seen that translations of the form W is AX really correspond to kind of translation in units. So if A is equal to 1,000 and W is 1,000 X, then if X is meters, then W is millimeters. And if X is in meters uniform from B to C, then W is going to be uniform in millimeters from 1000 B to 1000 C, right? This isn't surprising. But similarly, this same kind of units transformation doesn't change the kind of random variable you get for most of the familiar random variables we know. So for instance, if x is exponential with parameter lambda, then it's an example of, for exponentials that x typically was some kind of a waiting time. Right, so we might be measuring x in seconds, and w equals 1000x is the same measurement. It's the waiting time in milliseconds. So whether you measure this waiting time in seconds and it's exponential. If you measure it in milliseconds, it's still exponential. The only thing that has changed is that the rate parameter is divided by A, in this case by 1,000. So if you had 10 arrivals per second, now you have zero point zero 0.01 arrivals per millisecond. And the same thing goes for the Erlang. In the Erlang random variable, lambda was once again kind of a rate parameter. And if you change the unit by this factor of a 1,000, then the rate parameter goes down by 1,000. In the case of the Gaussian with parameters mu and sigma, we can think about uh, x being a voltage measured in volts, and then W equals 1000x is the voltage in millivolts. In the Gaussian case, we've actually been using this theorem for some time because when we chose A equal to 1 over sigma, then the standard deviation of W would be A sigma equals 1. It's the trick we use to convert any Gaussian to a normalized, standardized Gaussian with standard deviation and variance 1 so that we could look up CDF values using the phi function. So the textbook omits a proof of this theorem, and the reason it does is because, in fact, the theorem is simple algebra that follows from the PDF of W is 1 over A times the PDF of X evaluated at W over A. So, for example, in the Gaussian case, X has PDF. All of you should have memorized this for the midterm. 1 over the square root of 2 pi sigma squared, e to the minus x minus mu squared over 2 sigma squared. And then it follows that the PDF of W is 1 over A times the PDF of X, square root, evaluated at W over A minus mu squared over 2 sigma squared. And with a little algebra, you can rewrite this as square root of 2 pi A sigma quantity squared e to the minus W minus A mu squared over 2A sigma quantity squared. And this confirms that this is a Gaussian PDF with expected value A mu and variance A sigma quantity squared. Besides unit scaling, where you multiply by a constant, the other simple transformation that you see a lot is translation, where you take a random variable x and you add some constant b to it to get a new random variable w. And here the theorem is perhaps even simpler. It says that the CDF of W is the CDF of X just translated to W minus B, and the PDF of W is the PDF of X translated to W minus B. And this theorem actually is so simple we can just write down the proof right off the top of our head. It's CDF of W is the probability W is less than or equal to W, which is the probability that x plus b is less than or equal to w. And this is the probability x is less than or equal to w minus b. And that's just the CDF of x at w minus b. And then, of course, the PDF just follows by taking a derivative. So far, the problems we've worked on have been simple because they've been one-to-one transformations. For each value of W, there's exactly one value of X that can produce that W. Um, we have more complicated problems when we have functions that W, there's more than one value of X that can produce the same W. And this perhaps the simplest one, and the one that will help you understand it, is W equals X squared. So x equals 10 or x equals minus 10 produces w equals 100. And this fact that both positive and negative x map to the same w make finding the CDF a lot trickier. In this case, we need to go back to the graphical method that we discussed earlier in this lecture. Maybe then it seemed like an annoying pain in the butt, but here it really becomes essential. So here we think about the xy, the xw plane, and here is x, and x is continuous uniform from -1 to 1, so that we know it's on this in this interval, and now we plot the function w is equal to x squared. My plot is pretty bad, but good enough, right? And now what we do is we're interested in finding the CDF of W, and that's the probability that x squared is less than or equal to w. And here it helps to first knock out the simple cases. So looking at our plot, I noticed that I forgot to label some things. So this is the value 1. And so we see that uh, W is going to be between 0 and 1 because X is between -1 and 1. And so knowing this, we know that the CDF of W is going to be 0 for W less than 0. And we know that the CDF of W equals 1 for W greater than or equal to 1, precisely because we know that W, which is x squared, has to be between 0 and 1. So now we're just left with the tricky case when we have W between 0 and 1. So in this case, you mark a value of W along the axis W. And if we think about this graphical method, we're interested in observing a W that is anywhere below this, this little W of interest that we've marked. So the way to think of this problem is that we do an experiment and we generate an x between -1 and 1, and then that x is translated into a w, which happens to be x squared. And if you think about the x-w pair that's generated, that pair lies along this along this function, the bowl function corresponding to w is x squared. And specifically, um, uh, what's happening here is that if for w to be less than or equal to w, you can think conceptually of like there being a line here, and then that then gives us points, right? Where if w is below this value of w, then the xw pair has to be along this segment, and it says that the value of x has to be in this interval. And so now identifying the points of that interval, we have that we recognize that this corner point here is x equals square root of w and w, and this corner point over here is the corner point minus square root of w and w. And now we can translate that to down here, x is square root of w. At this far left extreme, x is minus square root of w. And what we see is that the probability w is less than or equal to w is the probability that x is between minus root w and root w. Now, the logic of this transformation of w less than little w is that x is between minus this root little w and root little w. That, in fact, holds for any random variable x. The next step is to realize that we have to then to do a calculation of what this probability is that's specific to the PDF of x. So here we have a PDF of x, fx of x minus 1 to 1, and the height is a half, right? And root w is between 0 and 1, so maybe here is root w. Here is minus root W. And the probability we're interested in is uh, is the probability of this area under the curve. It's the probability x is between minus root W and W. So we have W is less than the W. I'll change my, because I'm using the wrong color, W to W, fx of x dx minus root W to root W 1/2 dx. And this is in fact equal to 1/2 root W minus root W. It's equal to square root of W. So putting these pieces together, we have the PDF of W is equal to 0 for W less than 0. It's equal to root W for W between 0 and 1. It's equal to 1 for W greater than 1. And then we just take a derivative to find the PDF. Since we have a piecewise function, we do this derivative piecewise. And so the only piece that matters is W's between 0 and 1. And in this range, we get the derivative of square root of W is 1 over 2 square root of W. 0 less than or equal to W less than or equal to 1. And 0 otherwise. And then perhaps we should be a little more careful and realize that 1 over root W blows up at 0 and get rid of this. Getting rid of this doesn't actually matter because the probability x is exactly 0, has 0 probability. So this problem demonstrates that these derived random variable problems really have two steps. There's first, when you're finding the CDF of W, you translate that into a question about the CDF of X. But if X is given to you with a PDF, you then have to do some kind of an integration over the PDF to find the probability you're interested in. And then finally, of course, you always have to take a derivative to get the PDF of W. If you read the textbook, you'll find actually that this solution isn't what appears. In fact, the statement of this problem has a typo in it that makes this version of it much simpler. The problem in the book is, the solution in the book is solving a different problem. It's solving the problem when x is continuous uniform from -1 to 3. And that adds a kind of an extra level of complication in the following sense that these steps where you take the CDF of W and you translate it into the CDF of X stay the same. But this step where you do this calculation for W's between 0 and 1 isn't exactly correct anymore. So we'll step through the solution in the book to see how the solution for this problem with a different continuous uniform distribution makes things more complicated. Okay, so here is the textbook solution for x continuous uniform -1 to 3. And as I pointed out, that all of this is the same as what we did on the previous slide. The CDF of W is the probably x squared is less than W, and that's the probably x is between minus root W and W. All of this is exactly what we just did. The next step is the same, where you have to find the probability that x is between minus root W and W. You just integrate the PDF of x from minus root W to root W, same as before. Where things get tricky here is in the next step where we say, oh, x has a -1 to 3 PDF. So here is the PDF of x, and it starts at -1. It goes to 3, and the height of that PDF is 1/4. So, and as the words here state, the integral is somewhat tricky, which just basically means tricky, because the limits will depend on the value of W. In particular, because x can go from -1 to 3, W can go from 0 to 9. So the simple cases are, well, the CDF is 0 for W less than 0, and the CDF is 1 for W greater than 9. But how you do this integral will actually depend on W's between 1 and 9 in a non-trivial way. So in fact, so the first case is kind of simple. W's between 0 and 1. And in this case, we integrate from minus root W to W. And over that whole interval, the value of the PDF is 1/4. And so the CDF we're interested in is the integral from minus root W to root W of the value of the PDF is 1/4. And we have almost the same integral we had before. The answer is root W over 2, and it's not too complicated. The more complicated case comes up when W is greater than or equal to 1. And in this case, the structure of the integral, the defined integral, is still the same. Fw of W is minus root W to root W fx of x dx. But the problem here is that the minus root W is less than -1. And so there's a segment of this interval, of this integral that we're doing here, where the CDF, I'm sorry, the PDF, fx of x is equal to 0. So in fact, in this integral expression, this PDF only starts being non-zero at -1. So the lower limit is -1, and then we integrate up to W, and we end up with this area that was shown in gray, but I've reduplicated in pink, right? And the integral itself is actually trivial to do. We get root W plus 1 over 4. But it's only trivial after you realize that, oh, this lower limit is -1. So putting all these pieces together, we now have something a little bit complicated. So as before, the CDF is 0 for W less than 0. It's root W over 2 for W's between 0 and 1. It's root W plus 1 over 4 for W's between 1 and 9. And then finally, for W greater than or equal to 9, it's equal to 1. And if we take a derivative of this piecewise differentiable function, we get the two different derivatives, 1 over 4 root W here for W's between 0 and 1, and 1 over 8 root W for W's between 1 and 9. And we see that the PDF of W now has this very funny little bump. Just keep in mind here, even though the PDF has a jump here, a discontinuity, in fact, W is a continuous random variable because the CDF of W is continuous. You can check that the CDF of W at W equals 1 is equal to 1/2, whether you use this rule or the second rule. Going forward, the plan was to have one mini lecture for each section, and because the sections are usually short, the mini lectures should be short. But this mini lecture is already a little too long, but in fact, there's still more interesting material in this section. So we'll continue this in a part two of the lecture on section 6.2.